Welcome back to our next video. This is Dr. D.BHAKIARAJ, working as an assistant professor in Department of Chemistry, St. Joseph's College, Cuddalore. And in this video, we are going to see the optical isomerism of lactic acid. So before entering into lactic acid, let us see what is optical isomerism. So optical isomerism is a type of stereoisomerism. The outstanding feature of optical isomers is that they have the ability to rotate plane polarized light. So what do you mean by plane polarized light? So let us see. A nickel prism, which is made up of calcite, calcium carbonate or Polaroid lens, can able to polarize the light into one plane. The light passed through this nickel prism, which comes out from the nickel prism, is called plane polarized light. A molecule which have the ability to rotate the plane polarized light into either clockwise direction or anti-clockwise direction is called optically active compound. So this property is often referred to as optical activity and requires a brief discussion. Let us see. So the light comes out from the plane polarized light, nickel prism, is passed through the organic compound solution, and the resultant light comes out from the solution either rotated into clockwise or anti-clockwise, or as such it will come. The compounds which rotate or deviate the plane polarized light either of the side are called optically active compounds. So the compound which rotate the plane polarized light into clockwise direction are called dextrorotatory and denoted by the symbol plus, and the compounds which rotate the plane polarized light into anti-clockwise direction are said to be levorotatory and denoted by the symbol minus, and the compound which do not rotate the plane polarized light on either side are called optically inactive compounds. Let us consider lactic acid. Let us consider lactic acid. Lactic acid is nothing but 2-hydroxypropionic acid. 2-hydroxypropionic acid. 3 carbon atoms are there. So propionic acid. So in which at the second carbon, one OH group and one hydrogen is attached, and 3 carbon carboxylic acid. Hence it is 2-hydroxypropionic acid. So all the 4 groups attached to the center carbon atom are different. So this particular lactic acid shows optical isomerism because the center carbon is called chiral carbon, in which all the 4 groups attached to the central carbon are different. So the chiral carbon, wherever chiral carbons are there, the compound may possess an optical activity. So the 3-dimensional structures, possible 3 structures are shown in this here. So let us consider the one by one. These 3 structures, these 2 structures which are given in the below structure are not identical, but because they cannot be superimposed on each other. One is the mirror image of the other. Such non-superimposable mirror images are called optical isomers. So look at the structure. The carbon, OH group and hydrogen, all the 3 groups are present in the same plane. And in the left side first structure, the methyl group is pointing towards us and the carboxyl group is pointing away from us. In the second structure, similarly, the carbon, hydrogen and OH groups are in the same plane, and the methyl group which is pointing towards us and the OH group is above from us. So these 2 molecules are non-superimposable mirror images. One compound is the mirror image of other, But when you try to superimpose these two, these are non-superimposable mirror images. Such a non-superimposable mirror images are called optical isomers and are called enantiomers. Thus, for lactic acid, there are three possibilities. Three enantiomers are possible. One is dextrorotatory, another one is levorotatory, and another possibility is a racemic mixture which is optically inactive. So, one by one we will see. So, first, dextrorotatory. So, the molecule which rotates the plane polarized light into clockwise direction or right side direction are called dextrorotatory, and it is denoted by the symbol plus. Hence, the dextrorotatory lactic acid can be called as plus lactic acid. And the second, the other molecule which is nothing but the non-superimposable mirror image of the plus lactic acid. Normally, that molecule rotates the plane polarized on the left side, that is on the anti-clockwise direction, and hence it is called as levorotatory, and it is denoted by the symbol minus, and hence that molecule can be written as minus lactic acid. And as I already told, these plus lactic acid and minus lactic acid are enantiomers, and these two are non-superimposable mirror images. And the third one is plus or minus lactic acid. It does not rotate the plane polarized light on the either side. Hence, it is optically inactive. So, how it is possible? It is nothing but the equimolar mixture of dextrorotatory and levorotatory compounds. Lactic acid, 50% dextrorotatory lactic acid and 50% levorotatory lactic acid. When you exactly mix these two compounds, which is called as equimolar mixture of dextro and levorotatory forms, and this type of mixture compound is called racemic mixture. One half of the dextrorotatory molecules tries to rotate the plane polarized on the right side, and the other half of the 50% of the molecules tries to rotate the plane polarized on the anti-clockwise direction. Hence, since it is an equimolar, both the pulling power is neutralized, and hence the plane polarized light comes out as such without any deviation. Hence, this particular equimolar mixture is called racemic mixture, and the melting point of the dextrorotatory compound is 26, and the melting point of the levorotatory compound is also 26, whereas the melting point of the racemic mixture or equimolar mixture of plus or minus lactic acid is 18 degree. So, these are the three different forms of lactic acid. Hope this video will be useful for understanding the optical activity of lactic acid. Thank you.